In this video, we're going to cover Legendre polynomials. They're special polynomials that are used in a variety of applications. They're used for interpolation, and they're really nice to use when integrating things. And we're going to be looking at it from the point of view of a solution of an ODE system. So let's rewind a little bit. I know it was 2 weeks ago, but we saw while working on power series this specific example. So the solution of 1 minus x squared times the second derivative of y minus 2x y prime plus lambda y equals to 0. And we could write the solution as a power series when we define the coefficient of the power series in a recursive way. And the formula we found was this one, in which ak plus 2 is in a relationship with ak, and the relationship involves k plus 1, k plus 2, and lambda. Now, since we have ak plus 2 depending on ak, so we're jumping ak plus 1 when defining ak plus 2, we can actually split this series into two sections, the odd series and the even series. So all the even k's are summed up together, and all the odd k's are summed up together in another series. Then we remember that all the even k's, all the ak's with k even, are all something multiplied by the previous even k until we get to a0. So we can take a0 out of all the coefficients and just get it in front. With the same approach we can do with the odd series. So ak with k odd is a coefficient, depending on k, times a1. So we can take a1 out. As a result, we notice that our final solution, yx, is equal to the sum of a0 y0 and plus a1 y1, with y0 and y1 power series. And y0 and y1 are power series which terms depend on lambda. And if we choose lambda with some specific properties, with some specific values, we can make one of the two series terminate when we want. For example, if we find lambda equal to 0, if we go back, we notice that a2 is equal to 0 times a0. So y0 has only the a0 term, the 0th term. y0 is the constant 1. In general, where lambda is equal to n times n plus 1, then an is the last non-zero term. So depending on n, then an could be in the odd section or the even section. It doesn't matter, but that is the last non-zero term of that series. Then that block of solution is a finite polynomial called the Legendre polynomial, up to the constant we have defined. About this extra constant, a nice property when you're looking at function is that their integral is equal to 1. For Legendre polynomial, the integral is computed on the interval -1, 1. So we multiply the Legendre polynomial by a value in such a way that their integral satisfies this condition. So if we want to do some examples, we can choose, in the first column of this table, we choose which one is the last element that is non-zero. Then we determine lambda with the property we have set before, so it's n times n plus 1. Then we calculate the finite series, either the even one or the odd one, and we can compute the Legendre polynomial as the solution yx rescaled by a quantity that makes the integral between -1 and 1 equal to 1.